Alrighty. So, if you would please get your notes out, and we'll get into this final section that we have for ourselves. Okay. So, of course, the technique that we learned for estimating error yesterday, or to approximating error, finding the maximum amount of error, okay, because that's really what we want to find, the maximum possible error, okay, to help us then get a idea about where are the range of values, I guess, or whatever that we're going to approach. The key component, or one of the key components, right, is that not only, well, we had to be decreasing absolute value to 0, but we also had to be alternating, right? So what if, though, our series is not alternating? Well, it turns out we have an option, right? Okay, we must use something called Lagrange error, okay, in which our maximum error will occur at some value z, such that z is in between the x value that we're approximating with our polynomial function and c, the center, okay, the center about which we're building this polynomial and stuff like that, okay? So again, yesterday, right, we kind of took advantage of the fact that with an alternating series, all right, we start at a particular value with our first term, then we will either add or subtract to that, in this case because we started positive, and then we start with a positive thing, we add or subtracted, so we then subtracted, and by subtracting that next term, we're going to go through the actual term, right? And then by adding the next term, we're going to go still through the other term, subtracting, and so on and so forth, and the distance from the actual term is decreasing, bless you, as you go, so we're getting a better and better approximation, decreasing our error, okay? But at most, from the previous term, we'll be off by adding that next term, either adding or adding a negative, depending on a positive or a negative, depending on whether it was a positive or negative term kind of thing. Okay, so at most we'll be off by that much. But when we're not alternating, right, it kind of creates, we can't use that same kind of idea. Okay, and so the proof for that, well, we're not going to go through a proof for the Lagrange error. It's pretty complicated and messy according to the book. There is a proof for it in like the appendices if you wanted to like look back there and really get a handle on that. If you had some trouble falling asleep or something like that, you could go back and check there. Okay. Anyway, so here's just basically what we're going to be doing though. We're just going to kind of go through what the actual formula is. So Lagrange error bound, or Taylor's theorem. Okay. We're going to find, again, the error for a Taylor polynomial. Okay, so you can see here's our Taylor polynomial, right? And we know that this finite Taylor polynomial will equal our function plus some remainder. That's like the actual error and stuff like that. Okay. But here is how we're going to find the error for our Lagrange for a non-alternating series. Okay, and you'll see that what we're doing here is, well, it's very similar to what we did before. This is just we're still using the next term here. Okay. Still using the next term. Okay, right? We have this Taylor polynomial that goes up to degree n that we're using to then say is equal to the actual function f here. And so then to approximate that error, we're going to use the next term. Bless you, n plus 1, x minus c to the n plus 1. You'll notice, though, one of the big differences is that we have this little z here. Okay? And that is like the kind of like thing we'll have to be kind of solving for, we'll have to kind of figure out in order to estimate what our maximum error is here. Okay, so again, this is very similar to the alternating series remainder, or error, right? And that they both use the next term in the series. So that's something that's common. We don't have to memorize two different things in that case. They both just use the next term in the series. However, when using Lagrange error, you must find or use reasoning to determine the z value that will make the next derivative the maximum value possible. So this is where our work is going to be, determining the z value that will make the next derivative the maximum value possible. And the reason why I want to make the next derivative the maximum value possible is we want to cast kind of like the widest net, okay, for our error, right? We definitely don't want to underestimate our error, because when you underestimate your error, well then you don't want to be outside what your error is. We want to be within a certain error kind of thing. And so we want to cast the widest net possible, which means we want to then pick the z value that's between, again, the x value that we're approximating and our center, that makes that term, that error, kind of as big as possible. Okay, and then this will make the remainder the largest possible, and will truly represent then the maximum error. Okay, so let's see this in practice. All right, just because maybe it'll make more sense maybe when we actually do it. Okay, so given the function f of x equals 3 to the x, letter A, write the fourth degree Maclaurin polynomial for f of x and the general term. Okay, and we're going to use this fourth degree polynomial to approximate 3e squared. Okay, so go ahead. This is not new, so you guys go ahead and do that. All right, find the fourth degree Maclaurin polynomial for f of x being 3e to the x. Okay, and then also write the general term, and then use that fourth degree polynomial to approximate 3e squared. Okay, so I'll go ahead and do this here too. Yeah, that's why I sent you up there right now, because I don't want you to lose your position.
So you're
87 out of 90. Yeah, you're good. Yeah.
Did you already finish?
My mom did a lot.
If you turn your paperwork on already, yeah, you're good. Yeah.
I didn't know you could turn your paperwork in and then pay after.
Oh, well.
It's okay, I'm still in.
The online payment is harder for us to like confirm that it happened or not, I guess, kind of thing. So.
Sorry about that.
Oh no, it's okay that you did it.
It's my bad.
I'm glad you got it.
Lynn's just wild.
I love your mother.
Please tell me you don't call your mother by her first name.
Not to her face.
Okay. Unless she prefers it that way, in which case, whatever.
That would be strange.
I don't know. I feel like there might be cases of that. Okay. All right, so there's our fourth Taylor polynomial. Sorry, Maclaurin polynomial. We're centered at 0 here. My apologies. Okay. Just using the power series that we know for e to the x, right, but then multiplying by 3. And so the general term, again, would be the typical power series there. It's going to be 3x to the n over n factorial. Okay. And again, we're going to use this to estimate what 3e squared is. And what is 3e squared approximately? Anyone get that calculated yet? It's what? Using the polynomial?
Oh, no.
I was going to, yeah, use the polynomial if you don't mind. 21, yeah. So 3e squared is approximately 21, but let's go ahead since you gave it to us there. Will, what did you say what it was approximate? I mean, what is the actual value rounded, I guess, kind of thing?
22.1671683.
Okay, 1671683, like that?
Yeah.
Okay, perfect. And we'll hold on to that for right now. Okay, we can see currently we have a pretty good approximation, right? We're saying it's 21 with this fourth degree, and it's really going to be 22.1671683, so on and so forth. It keeps going, right? Okay, so that's nothing new right there, right? This is something that we've been doing, right? It's very typical for this unit. But then letter B, here's where the change comes in, the new stuff, right? Letter B, find the maximum error of this approximation to the actual value of 3e squared. Okay, what you cannot do here, of course, is just subtract these two things and say, the error is 1.1671683, right? Because again, we have to come up with the error approximation. Okay, we have to come up with the error approximation there. You giving the actual error is pointless because then you have the actual value, so what's the point of approximating in the first place, kind of thing. So anyway, find the maximum error. Okay, so first of all, it's important for us to recognize here, is the series alternating? No, okay, right, so the series is not alternating, so we cannot use the, what we did yesterday. Okay, we can't use the maximum error for what we did yesterday. Okay, so our setup here. Well, the setup's going to be very similar. So we're going to take, again, what the actual value is, and subtract the approximate. Okay, so actual minus the approximation. And according to the Taylor's theorem or Lagrange error bound, however you want to call it up there, according to this, that should be then less than or equal to the absolute value of, and then what was our n originally? What was our n from our sum here? 4. So we're going to go to the next term, so that will be 5, right? So it'll be the fifth derivative of f evaluated at z, and we're going to talk about how to find z here in just a second, all over n plus 1, so 4 plus 1, 5 factorial, okay, times, and in this case, since, what is our c value here? What are we centered at? 0, right? So we're just going to have x minus 0, or I'm just going to put x there, to the fifth, like this. So we, bless you, yes. We know what x is going to be. What's x going to be in this little calculation here? 2. X is 2, right? Because that's the value that we're trying to approximate at, is 2. So we're going to plug 2 in for x here. But it's z that we need to calculate, right? We go back up here to Taylor's theorem. We were told that z is going to be between x and c, okay? So let's just like a little side note here, all right? We need to maximize the fifth derivative of f at z, okay, where z is some value between our center, and we said earlier, right, center was c equals 0, okay, and x. Which is, again, x is equal to 2 in this particular case. Okay. So again, this is kind of like our thought process here. This is the setup, right? Very, very similar to what we did in the past. But in the past, it was just the next term evaluated at x. In this case, because we're not alternating, we have to come up with this z value here. That's going to help us determine kind of like the maximum error in this case. Okay. And again, z is going to be between our c value of 0 and our x value of 2. All right? Well, let's consider here our function. Right? So the function itself is 3e to the x. Okay? But we need to figure out what is, or I should say maybe not what. Let's say where. Where is the maximum value of the fifth derivative of x, which, by the way, what will the fifth derivative of x be here? Or will the fifth derivative, sorry, of f of x be here? 3e to the x, right? Woo, that's really nice, because if it was something more complicated, we would actually have to take the fifth, get down to the fifth derivative here. But because it's just nice and easy, 3 to e to the x, we can just say, aha, the derivative will be 3e to the x, right? Because it doesn't change as we take the derivative there. Okay, so where is the maximum value of this fifth derivative of x equal to 3e to the x? For, or between 0 less than or equal to z less than or equal to 2. Okay, so for that range of values, what's going to give us the maximum value? Okay, well, any ideas here? Between 0 and 2, what of those values is going to give us the highest possible value? 1.999. Well, we can include 2, so we can say 2 here. It's okay. So yeah, it's going to be 2, okay? What do we know about 3e to the x? This function is always what? Always increasing, right? So the right end point is going to be the highest in this case, okay? Now, it might be, if the function was always decreasing, then where would we go for where our maximum kind of value would be? The left end point, right? And of course, the function both increases and decreases. Well, we might need to go to the derivative of this to then identify, you know, where the maximum min was, the absolute maximum min was in that case, kind of thing. Okay. But in this case, okay, since e to the x is always increasing, then z equal to 2 will locate the max of the, the fifth derivative of f there. Okay, so that's quite a bit of writing there, but this is the idea. This is the kind of the idea that I wanted to have there for you. Okay. And this is where it gets a little bit trickier because it's not so cut and dry, right? The last problem, or the last kind of error calculations we were doing, all we had to do was just establish that the function was both alternating and decreasing absolute value to 0, and then we just would evaluate the function, at their particular x value. That's all we had to do. Okay, very straightforward. Here, there's a little bit more analysis that's required. We're not guaranteed a particular maximum at a particular location, right? We're guaranteed a particular, maximum error here. We have to figure out where it's going to be, again, using the function, or in this case, the fifth derivative of the function. Okay. So that's the idea. So now that we know that z is 2, we can say safely then that the maximum error, the maximum error here of 3e squared actual minus the approximation here will be less than or equal to the fifth derivative of f evaluated at 2. Okay, so z is equal to 2 there, over 5 factorial times, and again, I'm going to go ahead and plug in the x value of 2 there. What is f?
No, what is happening upstairs?
Oh, I don't know. Yeah.
Big party.
Big party.
So what I heard you threw parties in other classes, but not ours.
Yesterday? I did.
So we're at least party for a whole month.
I did. Right, exactly. So, it's for part of our project.
No. Don't explain.
Okay.
It's fine.
I won't. All right, anyway, so let's evaluate here. So plug in 2, right? So the fifth derivative of f at 2, well, we have that right here, right? So it's going to be 3e to the 2. So we'll say this is less than or equal to, so 3e squared over 5 factorial times 2 to the 5th. Okay. Which if we, give an actual value for this right here, let me do that here. So 3e squared divided by 5 factorial times 2 to the 5th. All right, and we get about 5.9112, we'll say. So that is our error approximation. Okay, max error approximation, I'll say. Okay. So, question.
Where did the 2 come from in the 0 is less than or equal to z on the side? Well, in our explanation.
Over here?
0, yeah.
Okay, right. So again, where does z come from? Z, okay, will be between your x value that you're trying to approximate at, and then the c, the center of the Taylor polynomial, or the Maclaurin polynomial. Since it's Maclaurin polynomial, we know it's centered at 0, so c is 0. And then our x value here, we're trying to evaluate 3e to the 2, so x is 2. So between 0, our center, and 2, our value that we're evaluating at. Okay? And I think kind of like the idea is, we're centered at a particular point, and then we're building this, if you remember, like big picture, we're kind of building this polynomial, right, centered at a certain point. So it's centered at 0 in this case. We build this polynomial. As we build the polynomial out, right, we will build it closer and closer to that 2, and so our value for z there, well, it's got to come from an x value between 0 and 2 there. Is the idea. We're going to find that. Okay, we're building from 0 to 2, so we need to pick some x value there that's going to, again, guarantee the maximum value. All right, so does this maximum error kind of fit our scenario? Well, remember earlier, right, Will gave us that 3e squared approximately was 21 using our p sub 4 there, right? Okay, that's, equal to p sub 4 at 2, okay? And then he gave us the actual in the calculator, and the difference here was like 1.1671683, okay, right, to subtract them. Whereas here, we said the maximum error was 5.9112, so is this true? I mean, is this maximum error? Well, yeah. In this case, this says we're going to be at most 5.9112 off, and in fact, we are only 1.1671683 off. Okay, so we were well within our maximum error there of 5.9112. Okay, so questions on any of that? Yes, well.
In the approximation, didn't we use 3e squared? The values we're supposed to find to approximate.
So right, yes, and that is kind of I don't know what I want to say, but yes. The thing that we're trying to approximate is in the error calculation itself. So it's like, how are we supposed to? Yeah. How are we supposed to use this if it's already in the thing? So you're right, yes, it is, but that's what we're doing, okay? So yeah, that's it. Yep. The thing that we're trying to approximate is in the error calculation itself. Neat. Okay, so, but that's what we're doing. That's what we're doing here. Okay. Do you have a question, Mike, or you just want to try another one maybe? Let's try another one, okay. All right, so let's flip over here. Number 7, all right, the function f of x equals 1 over the quantity 1 minus x squared can be expressed as the series, the sum from 1 to infinity of n times x to the n minus 1 for all values of x within its interval of convergence. Okay. Find the interval of convergence of f of x. Okay, so, how do we do interval of convergence again? What are we supposed to do here? Okay, ratio test. Right, yeah, this is not geometric, right? This is not geometric. Okay, this is just a ratio test we're going to use here. So we're going to do the limit then. As n approaches infinity of the next term, so which is we're going to use in our series here. So, and I'm not going to do the multiply by the reciprocal thing because we have just a nice, kind of term right there. So I'll just make it n plus 1 times x to the n, right, yes, x to the n, right. When we put when we add 1 to our n here, we get n plus 1, but it's n minus 1. Adding 1 to that, you get just n. That's going to be all over then n x to the n minus 1, absolute value there. And we want that to be less than 1, right? The ratio test. All right, so we'll simplify that a little bit. We get n plus 1, and then, let's see here, we get x over n like that. Okay, and which is less than 1. And what will this n plus 1 over n do? It will equal 1, right? Again, if you wanted to, if we were like trying to show all of our work for free response questions, stuff like that, we'd say apply L'Hopital's because it's really infinity over infinity. You take the derivative of the top and the bottom with respect to n, you get 1x over 1, and then you can say, aha, it's just going to be the absolute value of x. But we're going to just skip through that part and just say, okay, so this goes to 1. Okay, so we'll just say the absolute value of x is less than 1, which means our interval is from -1 less than x less than 1, like that. Okay. If we wanted to, right, we could identify the center here. What is the center? What are we centered about? C is 0. Okay. If we wanted to here, we could also identify the radius of convergence. What's the radius of convergence? R equals 1, right? We're 1 away from the center in either direction. Okay, so we're done, right? Good. Right, what do we still have to do? Test the endpoints. Hooray. Okay, so that's the sum from n equals 1 to infinity of n times 1 to the n minus 1. Okay. And so 1 to the n minus 1, that's just 1, right? It's just going to be a positive 1 there. So that's equal to really the sum from n equals 1 to infinity of n. And what do we know about this? It's going to diverge or converge? I heard both answers here. So anyone want to say why? Converge, diverge? We need a reason though.
P-series is less than 1.
Is this a p-series?
No. Well, you can put it.
It's going to be 1 over. Oh, I see what you're saying. It's 1
over
n to the negative 1.
Can you do it like that?
Hang on. Okay, we could think of it like that, sure. Since this is less than 1, what would a p-series do then? Diverge goes that way. Right, but we can also do the nth term test for divergence here too. Just take the limit as this thing and approach infinity. The term is going to get bigger and bigger and bigger. And we're going to keep adding, larger and larger numbers, right? This is maybe so simple that it's complicated now because we're used to doing the more hard things. But we're just adding up an infinite number of numbers, and they keep getting bigger as we go. So of course this quantity is going to diverge.
Can't you just also use geometric from the beginning?
Can we also
Because
use
it's
geometric?
a value to the n.
That's what you're saying. Yeah, we could have done that. Yeah, just a geometric series there. Mm-hmm. Yep, that's true. That's true. And that since it's 1, we know that will diverge. Yeah. All right, let's do the negative 1 here. See what happens. So here we get n times negative 1 to the n minus 1. So now we're alternating, but what's still going to happen here, though? It's going to diverge because if we try to apply the alternating series test here, if we take away the alternating part and you take the limit as n approaches infinity, it's not going to go to 0. It's going to go to infinity. So we're going to add increasingly larger positive and negative, or increasing more positive and more negative numbers, and so it's going to just diverge again. Okay, so our interval convergence turned out to be negative 1 to 1 without adding any additional points there. Okay, so letter B here. Use the first 4 non-zero terms of f to approximate the value of f at 1/3. Show that this approximation differs from f of 1/3 by less than 3/4. Okay, so we're going to use, again, our series here. The function, right, can be expressed as the series, this, and so we'll just go ahead and write it out. So f of x is approximately going to be, and then let's see, the first term here will be x to the 0, so just 1, I guess I should say there. And then, let's see here, 2 will be 2x to the 1 plus 3x to the 2 plus 4x to the 3rd. Mm-hmm.
Isn't there a multiple times n?
Yes, so it'll be 1 times x to the 1 minus 1, so 1, yeah. Okay, and then we'll use this to approximate f of 1/3. Excuse me. And I'll just go ahead and do this in the calculator here. Store x, 1 plus 2x plus 3x squared plus 4x to the 3rd. So it is 2.148 with the 148 repeating, it looks like there. Okay, or 58/27 if you like, if you're into the whole fraction thing. Okay. Remember, folks, if you're going to be repeatedly entering in the same number, 1/3 repeatedly, you can do 1/3 in your calculator, hit the store button, STO, and then store it in for x on your home screen there. And now whenever you use x on your home screen, it'll include 1/3, and then you can just type in 1 plus 2x plus 3x squared plus 4x cubed, just like that. Hit enter, and then it gives you your value like that instead of having to type in all those 1/3 and things. Just as a little shortcut there. Okay, so let's set up our error then. Okay, f of 1/3, the exact value, right, the actual value, minus our approximation, which we'll say is 2.148, repeating like that. Okay. We know that its error will be less than or equal to, and again, the next term. What will our next term be? What will the degree of our next term be? It'll be 5th, right? Okay, or sorry, 4th. 4th term. Okay, we're going to go to the next term, so that should be, oh, wait a minute here now. Yeah, it should be 4th term, the 4th term. Okay. So we'll do that here. Make sure I got this right here. 4th term. Oh, I'm sorry. So it will be okay. Sorry. It'll be a 4th degree, but it'll be the 5th term. I do need to watch what I'm saying here. Yeah. So we did the first 4 terms, so it's going to be the 5th term, but it'll be the 4th degree. Okay. So my apologies there. Yes. So you were right, Sarah. It was the 5th. Okay. So it'll be the 5th. Derivative of f there. So 1, 2, 3, 4. So the next term will be 5, and will be 5. This is, well, hang on a second. This is n equals 1, 2, 3, 4, and the next term should be 5. So it should be a 5 there. Okay, of z, all over. Okay, and then 5 fact. Hold on here. Use the next term. 5m plus 1, right, okay. 5 factorial, and then x to the 5th. Like that. Okay. And x is going to be a third, right? Okay. So we know x is a third. Now we have to figure out what that z is. Okay. So in other words, what value z, 0 less than or equal to z less than or equal to 1/3. Okay, because again our center is at 0, our x value there is 1/3, and so we want to be between 0 and 1/3. Will make the 5th derivative of f at x a maximum. Well, so here, right, we need to really kind of consider what this 5th derivative is, what the fifth derivative will be, right? And so if we have the original function here, this is where we actually have to take these derivatives, right? Because it's not so easy for us to kind of like mentally kind of do it. Maybe it is, maybe it isn't, but let's just do it here like this. So I'm going to rewrite f as 1 minus x to the negative 2. I think it'll be easier to do the derivative of that than trying to do a quotient rule every single time kind of thing, because in its original form it would be a quotient rule. So let's go ahead and take the derivative here. So the negative 2 comes out front, right? 1 minus x times negative 1, and so it's really then positive 2, 1 minus x. Oops, I forgot to the negative 3 there. Okay, again, by the chain rule, we brought the negative 2 out front, lower the power by 1, but then multiplying by the derivative of what's inside. The derivative of 1 minus x is going to be negative 1. So that's why we have to have the negative 1. Okay. And then f prime prime, the second derivative, right? We'll bring that negative 3 out front. Becomes negative 6, 1 minus x to the negative 4, but then again multiply by negative 1, so it really becomes positive 6. Okay. And so we're going to see a pattern here, right? F prime prime prime, third derivative, negative 4 times 6, negative 24, 1 minus x to the negative 5, but again multiply by the derivative of what's inside, becomes positive 24 in front. So the fourth derivative will be, let's see here, positive 120, 1 minus x to the negative 6th. And then the fifth derivative of f, oh goodness, 6 times 120, 600, 120, 720? Yes, good. 1 minus x to the negative 7. Okay. So what can we say about this function here, the fifth derivative of f? It will always be, so it's always going to be increasing, right? And then maybe if you're not sure about that, if you're like, how are we supposed to know it's always going to be increasing? Well, imagine taking the derivative of this thing one more time. Okay, the sixth derivative will always be positive, right? Because you're going to end up with some positive number, some positive coefficient, right? And then it's going to be 1 minus x to the 8th, well, negative 8, but it'll be an 8th power kind of thing, and that will always be positive. Okay, so it's a positive divided by something that's always positive, so it will always be positive. Okay, and so since the derivative of this will always be positive, I mean, if you want to, here, I'll just go ahead and write it out. Maybe that's not a bad idea. So 7 times 720, we get 5,040 to the 1, or times 1 minus x to the negative 8. So this will always be positive. So it's always increasing. Sorry, so f of 5 is always increasing. Okay. So long story short, right, where is z going to be at a maximum? Or where will the function f, where will the fifth derivative of f be at a maximum? When z is at 1/3, right? 1/3 here, the rightmost endpoint. Okay. So again, since that fifth derivative, we can see it's always going to be increasing. So therefore, the maximum value here will be located at the right endpoint. Okay, where that maximum value is going to be. So we'll go ahead and put this all in. The fifth derivative of f at z means we're going to be taking this function here. Okay, so that's going to be 720 times 1 minus, and then our z value here we're going to plug in is going to be, like I said, 1/3. 2 again, the negative 8 there, all over 5 factorial. You're right, I went too far. Thank you, negative 7 there. Okay, all over 5 factorial times, and then x to the 5th, and our x here, of course, is also going to be 1/3. Okay. To the 5th. Thank you. And so at this point, I'm going to just type this into our calculator because it's pretty messy. So and I get about 0.422, I guess I'll say. 0.422 is what I get there. And I guess I could just do the whole thing. It's really, 0.421875. Okay? Whew. So there's our maximum error, but that wasn't the final question, right? It says, show that this approximation differs from f of 1/3 by less than 3/4. Is this less than 3/4? Yes, it is. Okay, so check it works. Maybe I'll write down here. So z equals 1/3. Okay. Questions on any of that? One more here, folks. One more. Try to savor this moment here, okay? Try to savor this moment. Any questions before we move on to this last one here?
When's the test again?
The test is Tuesday of next week. Tuesday of next week.
Mike, you're gonna do great. You're gonna be all right.
This is the last page of our last pack.
Last page, last packet of notes. That's right.
So we won't have to take notes anymore in this class?
I mean, potentially you'll be, writing things down for yourself when it comes to the review. Like we have like pages for you to write. Like here's what I suck at, and then you list out these things on your page, and then these are things I need to study. And hopefully you start to cross things off that list because you no longer feel like you suck at those things.
We're gonna go in for a review to determine whether or not we suck at it or not.
So we're going to have, like I said, a practice test. So next week it's going to be both our final test for like the new material on Tuesday, and then Wednesday, Thursday, Friday will be AP test practice in class. Why 3 days? Because there's really 4 sections: calculator multiple choice, non-calculator multiple choice, calculator free response, non-calculator free response, and we can't fit all of the free response questions in on one day. So we'll have you'll do some at home for homework, we'll do some in class, and then Thursday and Friday will be multiple choice days. Multiple choice, non-calculator, multiple choice, calculator, kind of thing. Yes, that gives us our baseline, kind of like where you are right now without any studying, kind of thing. Okay, and I really do expect a range of scores from 1 to 5, kind of thing.
Is the lowest score you can get like a 60%?
4 to 5.
Oh, I see what you're saying. I forgot to ask. I'm pretty sure a 5. I'm pretty sure we're thinking. I think we said a 5 is a 100. A 4 would be a 90, and then on down, kind of thing. So 490, 380, 270, and then a 1 would be the lowest could go to 60, kind of thing. But of course, that's why I put the Saturday test up there. The Saturday test will replace, your test grade, and on the Saturday test we'll have more review under our belt. So ideally, you should improve, and then you can just replace that lower test grade and stuff like that. What's the curve for an AP test? So the curve, I don't know. All I can say is for the 5, right? So for a 5, you need you want to shoot for like a middle 60%. So like on the AP test, a middle 60% gets you a 5, or higher, of course. I hope so. People do, and I feel like the AP people will like tweet out names of students that do that kind of thing. It's rare for students to get 100%. Because, inevitably you'll end up missing a point on like a free response question or something like that, because, they can be very, idiosyncratic about like, oh, you didn't say this little word here, so you don't get full point for your explanation there, kind of thing. So,
I wouldn't care.
well,
Or
no, he was like
99%.
just
No, no one here that I know of. There was a Middletown student, I think, that got a
Oh yeah, Mr. Golf
100%.
has that one
Name
wall
of Jesus
dedicated to
Christ.
that.
Right. Well, that's just for double fives, not for people that got 100%. It's just if you got two fives.
Didn't
That's,
he say, I think he has one, like a separate wall that hasn't even been signed yet. That,
oh, for like the 100%.
Like
Oh.
with the wall, the doors.
Oh, okay. Oh, okay. Well, there you go. So,
See me
yeah.
there?
I don't even know what I'm gonna do. I don't have blocks. I have just like
You have
wall.
sand tiles.
So I do.
That could be like
I
one
do.
class.
I feel like I've heard in the past. Someone told me before that like you're not supposed to make those. Now, granted, I know other teachers do, but we'll see. I might still try and just like do something on the back here, kind of thing. We'll figure something out. Maybe I'll just make blocks or something. I don't know.
Yeah.
What?
Like paint. I don't know.
How
what
would
I'll
you do it?
I don't know. Like a stencil maybe or something. Ugh. Yeah, I don't know.
Tape.
I might just give you like like you can just put it wherever you want, but you get just like a border and you can kind of like position it however you want, but you get like a rectangle of space to work with or something. But it can be kind of
Tape the
wherever.
grid.
Just tape a grid.
And tape a grid. Is it gonna bother you if I don't tape a grid? Well, we'll see. This is way in the future here. Let's finish these two problems, all right? So we can get to your homework or this part A, part B. Okay. So another way that we're going to potentially need to be able to do this, of course, so we kind of went through a couple, processes here, a couple of different, variations of the problem. One, right, we took a familiar series, which is e to the x. We had to build the 3 e to the x from our known power series, and then we found the error, right? So that's kind of like one variety of problem. Oops, I'm pointing to things and it's frozen. Sorry. So again, just kind of give you guys an overview of the kind of problems you'll be expected to be able to do, right? So here's a typical kind of problem where we're taking a power series and then we build the given function based off the known power series, right? We know e to the x, we build 3 e to the x by just, multiplying e to the x's power series by 3, right? And then we found the error that way. Or sometimes we'll be given a function whose power series we don't know and can't figure out, and then we'll be given the power series, right? And then it's up to us to then, do some work. Maybe we'll write out, the first couple terms or something. In this case, we just had to find the interval convergence, and then we found the error that way. And then sometimes we'll also be just given a graph, and from the graph, we'll be asked to then, kind of pull some information out. We haven't seen a whole lot of graphs with this stuff, so this is a little bit different, but it's not too awful. So let the function f be defined as f of x equals x squared times e to the x squared. Okay. The graph of the 7th derivative of f can be seen below. So this is not the graph of f. This is, 7th derivative of f of x. Okay, so that's what this is right here. All right, letter A asks us to write the first 4 non-zero terms and general term, for the Maclaurin series for e to the x. Then we're going to use this series to write the first 4 non-zero terms and general term for the Maclaurin series for f. All right, so we all know what e to the x is, right? 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial. And we want the first 4 non-zero terms. So 1, 2, 3, 4, I'm done. Okay? Then we're going to use this series to write the first 4 non-zero terms and general term from the Maclaurin series for f. Okay? So let's see here. We need to build from e to the x. We want to build up to x squared e to the x squared. So what should be maybe the next thing here that we do? Put in the x squared into the power, right? So let's make it not e to the x, let's make it e to the x squared. And so that means all of the x's here, they're going to get replaced with x squared. So instead we have not x, but x squared over 1 factorial. Not x squared over 2 factorial, but x squared squared, so x to the 4th over 2 factorial. And then not x cubed over 3 factorial, but x squared cubed, so x to the 6th over 3 factorial. Oh, I forgot to write the general term here too. Sorry, because it did ask us for the general term as well, so I'll write that out as well. So that was, of course, x to the n over n factorial. Okay, and so what would our new general term be? We had x to the n over n factorial for just e to the x. What would the general term be for x to the, or e to the x squared? What would that be? X to the 2n. Yeah, exactly right. We just replace the x with an x squared, so it gets raised to the n power as well. So there's that. All right, and the last piece then, what are we supposed to do with e to the x squared? It gets multiplied by x squared. So we'll do x squared times e to the x squared. And so we get 1, or just x squared there, I'll say. So x squared plus x to the 4th over 1 factorial plus x to the 6th over 2 factorial plus x to the 8th over 3 factorial plus dot 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 plus, and then we're going to multiply by x squared, but there's already an x to the 2n. Let me go ahead and just do it this way. I'll just write it out. Okay. Since these both have a base of x, right, what can we do with our exponents? Add them. So this is really x to the 2n plus 2 over n factorial. Okay. And so this whole thing here is approximately our function there, f of x. Okay. So, questions on any of that? That's, again, it's pretty straightforward stuff we've been doing, right? Nothing new there. That's old stuff. Letter B, though. Let p sub 6 of x be the 6th degree Taylor polynomial for f about x equals 0. So let's just stop and think about that. Let p sub 6 of x be the 6th degree Taylor polynomial for f about x equals 0. Well, we just wrote a Taylor polynomial for f. Okay? What degree is our Taylor polynomial that we wrote? 8. We need a 6th degree Taylor polynomial for f. So what can we do with our answer here? Just take off the term with the x to the 8. Right. We just need this piece of our Taylor polynomial. So all we need is this right here. We can throw out the rest. Okay. So that's all we need to do. Find p sub 6 of 1/2. Okay, that's pretty easy. We'll just do p sub 6 of 1/2, which is 1/2 squared plus 1/2 to the 4th over 1 plus 1/2 to the 6th over 2 factorial. Okay, I'll just go ahead and type that in my calculator here. Squared plus x to the 4th plus x to the 6th over 2 factorial. Okay, and I get about 0.3203125. Okay, let me see if I can make that a nice fraction here. 41 1/28 if you like fractions instead. Okay. All right. So we're going to now approximate and then use the Lagrange error bound along with the graph to find an upper bound on our error here, right? So you can see there's our, now notice this, they did approximation minus the actual here. Okay. Is that going to change what we do? No, because it's in the absolute values there, right? So it doesn't matter. The difference, we're trying to just find the difference between the actual and the approximation here that we're using, and we're trying to find that error, right? So we're approximating that error. So it doesn't matter whether you subtract actual minus approximation or approximation minus actual. Don't worry about that. Okay, same thing. So in fact, I'll just go ahead and keep with that. Whoops, I don't know why I put that one. Should be absolute values there. P sub 6 of 1/2 minus f of 1/2. Okay, we know that's got to be less than or equal to. Okay, and what's our next term in this case? What degree would it be? Or what's n going to be? I shouldn't say degree. What will n be? 7, right? We had a 6th degree, or 6, n was 6 here, and so then we're going to go to 7. Okay. So f, 7th derivative of f at z over 7 factorial, x to the 7. Okay, so there's our setup, and now we know what x is already, right? X is going to be what? 1/2. We just got to figure out what z is. Okay, so again, I'm going to write some stuff out here. Find z. Okay, again, 0 less than equal to z less than equal to 1/2 between, again, our c value of 0 and our x value of 1/2. That will make the 7th derivative of f a maximum. But we don't know what the 7th derivative is. All we have is this graph of the 7th derivative. Okay? All we have is this graph of the seventh derivative. Where is the maximum going to be? At what? At 1/2. Exactly right. I mean, just look at the graph. This is the graph of f of the seventh derivative of f. Okay, at 1/2, we are the highest point right there. Okay, that's the highest point. So that's going to help us maximize our error for the most there. And so according to the graph, okay, of f, the seventh derivative of f, I keep wanting to say f prime prime. I'm not going to do that. That's too many primes. Seventh derivative of f at x, okay, z equals 0.5 would make, okay, the greatest value. Okay. So in other words, z, we want that to be 0.5. Okay. So what is the value of the seventh derivative of f at z? 500, right? Yeah, if you look up there, okay, right, at 0.5, we go to the y value of 500. So this seventh derivative of f at 0.5 is going to be 500. So we're going to be less than or equal to 500 over 7 factorial times, again, x here is 1/2. So 1/2 to the 7th, like that. And again, this is the approximation of the actual error. The actual difference between our approximation and the actual value. Okay. So we type this mess into our calculator here. Oh. And we get approximately 7.750, I don't know, 5, I guess I'll say, times 10 to the negative 4th. Okay. And so there is our maximum error.
Yep, I could have called it.
Got it. Meant to math that. Okay. One thing I do want to point out here, when you are using a graph, okay, when you're using a graph, all right, and let's say, for example, here that, I don't know, that you weren't, maybe the maximum value didn't occur at 0.5, or I guess really what I should say is, if you're going to use 0.5, all right, so we know that 0.5 has a maximum value here. Let's say maybe you weren't sure, it's like, I don't know if this ends up, you know, it's somewhere between 400 and 500. You can go ahead and just round up to like the higher value there. So in other words, if you are, you know, trying to locate the maximum value and you're like unsure visually about like what the highest y value is, you think it's like between two numbers, pick the higher of the two, pick the greater of the two, right? Now it's pretty obvious here that at 0.5 we're going exactly to 500, but if it were like, if it weren't quite clear, pick the greater of the two y values, so that way, again, you're accounting for, you're casting the widest possible net, you know, to kind of account for, I guess, the greatest range or whatever. Alrighty, so questions on any of that? So very similar to what we did yesterday, just we have to find that z value there, that's all. Okay,
We did it.
that's it, we made it.
Completely done with the
Okay, yeah. Okay,
Hey.
so don't cry because it's over, smile because it happened.